Hey guys, welcome back to a new video. In this session we'll be looking at circular motion and specifically the acceleration in circular motion. Because this is a topic that is oftentimes considered confusing and quite difficult, we'll be looking at it step by step. In particular, we'll be looking at the three different types of acceleration that can be present. And as you probably know, one of them, the centripetal acceleration, always has to be present if you have circular motion. As always, if you have any questions or suggestions along the way, leave a comment in the comment section below. You can of course also join the new Discord server where you can freely interact with fellow students or myself about any questions or discussions you might have. The link of this Discord server and to all other related videos about this topic can be found in the comment section below or the description of this video. And with that, let's dive right into it. Before we in detail address these three types of acceleration, let's first have a brief recap of what circular motion actually entails and what its fundamental quantities are. As you probably know, circular motion is the motion along a circular trajectory. And what the fundamental quantities are of this circular motion is of course the radius of our circle and the angle theta over which we have traveled on this circular motion. And all of the other quantities that you know about circular motion can be derived from these two parameters. For example, there is the arc length s, which basically is the piece of the circle over which you have literally traveled in your circular motion. And because this is a piece of a circle, it is also called an arc length. And this arc length might seem like a fundamental parameter, however, it can easily be written or derived from these two fundamental parameters that we have, r and theta. And this relation is encapsulated in the formula that s is equal to r, the radius, multiplied by theta, the angle that has been crossed during this part of the circular motion. And the reason why this formula is valid, I will leave for another video, of which you can find the link in the description below. If we are now considering a very tiny piece of the circle, so just a very small piece of circular motion, we can rewrite this formula for these infinitesimal changes as ds being equal to r, because r doesn't change, d theta, so the infinitesimal change in angle. And this formula, written in its infinitesimal form, can be used to derive a formula for the velocity of our circular motion. Because evidently, if we are moving in a circular motion, that means that we of course have a velocity. And this velocity, as you know, will be tangential to the trajectory itself. So let's say that we have our initial velocity here, vi, and then at this point we have our final velocity, vf. And in uniform motion, the velocity along the trajectory is constant. So we're moving in a circular motion at a constant velocity. And since this is just a velocity, it will be the same as if we were traveling in a straight line. And this is the change of position with respect to the change of time. And in this case, the change in position will of course be along this circular trajectory, ds. We can now, of course, rewrite this using the formula that we found here, which says that ds is equal to r multiplied by d theta. And then, of course, we still have to write this dt. So now we've rewritten our velocity along the trajectory as a function of how the angle changes with time, because how the angle changes with time is more fundamental. And I will touch upon this later on of why this is. And we write this change of angle with respect to time, the angular velocity, and we denote this with the Greek letter omega. And this brings us to the fact that the velocity on a circular trajectory is simply the radius of the circle on which we are traveling multiplied with the angular velocity. And thus here we see that with circular motion we basically have two velocities. The first one is just the velocity along the trajectory, which can be written as the change of position over time, and we have the angular velocity, which can be written as the change of the angle over time. And these two, as we saw before, can be connected by multiplying with r. And we can see this in the following way. Let's again look at our sketch. If the angle changes at a constant rate, let's say for instance 1 revolution or 2 pi radians per second. Then we know that if we were standing here compared to the center of our circle, that our velocity through space on a circular trajectory will be much slower than if we would be standing further away from the center. And why is this? Well, because if we are standing further away from the center, because the angle changes at 1 revolution per second, we need to travel a longer distance because our circle is literally larger in 1 second. And because this velocity through space, this first velocity, is dependent on where you are compared to the center of the circle, we consider the angular velocity as a more fundamental property, because the angular velocity clearly does not depend on the radius of the circle. And so now that we had a brief recap of the fundamental quantities of circular motion, let's now look at the 3 types of acceleration that can be derived from these fundamental quantities. The first type of acceleration that can occur is angular acceleration. And as the name already suggests, it's when the angular velocity changes in time. So let's see what this actually means. To do this, let's again draw the circular trajectory on which we are moving with radius capital R. Let's now say that after 1 second, we have traversed the angle theta. And concretely, for our circular motion, this means that we have traversed on this circular trajectory from point 1 to point 2 in 1 second. So let's write this down. So from second 0 to 1 second, we have traveled over an angle alpha, and from this we can derive our angular velocity, our initial angular velocity, to be exactly 1 theta per second. Let's now say that in the subsequent second, we are traveling a much further distance. So the angle that we traversed in the subsequent second is an angle beta. And this angle evidently is larger than the angle that we traversed in the first second. This means that in this second period, we traversed a much further way along our circular trajectory. So from second 1 to second 2, we traversed an angle beta. And therefore, we can derive that in this second period, our angular velocity is actually larger than our initial angular velocity. And therefore, we conclude that in this circular motion, there is an increase in angular velocity. And we know that an increase in velocity, no matter what kind of velocity, can be written as an acceleration. And in this sense, we have, of course, the angular acceleration, which we denote as being alpha. And of course, this is simply the change of angular velocity with respect to time. And this is, of course, the first formula that we find for the first type of acceleration, namely angular acceleration. The second type of acceleration in circular motion is tangential acceleration. And as you might expect, it is very closely related to the previous one, angular acceleration. And more specifically, in the same sense that tangential velocity is related to angular velocity. And we'll see exactly how in a minute. Let's again draw our circular trajectory with radius r along which we are moving. And instead of now looking at the angle that we traverse during the first second, we're going to be focusing on the actual motion through space along this trajectory that we are covering. Let's say that we start in point 1 and we end up in point 2 in 1 second. And let's say that the distance along this trajectory, so the arc length, we again note as s. And since we are moving, we of course have a velocity which we denote as vi, being the initial velocity. And let us now look at the distance that we traverse during the subsequent second. We see that the distance along the circular trajectory, so the arc length, which we now denote as s prime, is actually a lot larger. And this is of course only possible if our tangential velocity also changed. Concretely, this means that at this point, our new initial point, our tangential velocity, so the velocity that we actually have through space, is larger than our initial velocity. So let's write this down. If we went from the 0th second to the 1st second, we traversed an arc length s. And from this, we of course can derive the magnitude of our initial velocity as being s distance in 1 second. Now, if we look at the subsequent second, so if we start at 1 second and we go another second, then we see that we traversed s prime. And from this, we can calculate a final velocity, which we have over this second period. And from this, we see that our tangential velocity increased. So there was a change in velocity. And as we know, a change in velocity comes with an acceleration, namely the tangential acceleration of this circular motion. This acceleration can be written as the change over time of our tangential velocity. And from the brief recap from this video, we know of course that this tangential velocity is equal to the change of our trajectory s over time, so ds dt. And using the formula that we also saw in the brief recap, we know that ds is equal to r d theta. So we can rewrite our tangential acceleration as being the following. So ds we replace by r d theta. So we have r d theta divided by dt, of course. And since r is the radius of the circle, which of course remains constant over the entire process, it can be brought outside. And we remember that d theta dt is the angular velocity omega. So we have that this becomes r of the time derivative of omega. However, in the previous type of acceleration, we exactly saw that the change of the angular velocity, so d omega dt, is exactly the angular acceleration. So we see that this is simply equal to r times the angular acceleration alpha. And from this, we can observe a very nice pattern. We saw that the tangential velocity, so the velocity that we actually have through space along our circular trajectory, is simply equal to the radius of our circular motion, so the distance to the center of the circle, multiplied by the angular velocity, so the rate at which the angle changes. And we now found that the tangential acceleration is equal to r again, multiplied with the angular acceleration, so the rate at which the angular velocity changes. And it is in this way that looking at the tangential velocity or acceleration is very closely connected to looking at the angular velocity and acceleration. And this is why either one of the two are often neglected. However, as I said at the start of this video, the angular velocity and the angular acceleration are actually a bit more fundamental, since they do not depend on how far removed you are from the center of the circle. Let's now go to the third and final type of acceleration, the centripetal acceleration. And because this one is so different from the previous two, it is often considered as very vague or confusing. And in particular, because it will be always present in circular motion, even if the tangential velocity does not change. So even though the other two types of acceleration are zero, the angular acceleration and the tangential acceleration, the centripetal acceleration will always be present. And the reason for this being that the direction of the tangential velocity constantly changes. And in just the same way that changing the magnitude of a velocity requires an acceleration, a change in direction of velocity also requires an acceleration. This is a very subtle topic to understand, and because of this, I've made a dedicated video to show why this acceleration needs to be there and why it always has to point towards the center of the circle. So we'll not be covering the direction of the centripetal acceleration here, only its magnitude. And to do this, of course, let's again consider our circular trajectory with a radius r. Let's say that in this case, we're only considering a very small change along this trajectory, in a sense that we can write the change in angle as d theta and the change in position along this trajectory ds. And let's consider the velocity at both of these points. So we have vi here, and at our endpoint we also have vf, the final tangential velocity. Now, because we're looking specifically at uniform circular motion, meaning that the magnitude of our velocity does not change, both the magnitude of vi and vf are equal to each other, which translates of course to the fact that both of these arrows are of equal length. We see of course that the direction of the tangential velocity changed. First it was pointing in that direction, and now it is pointing in that direction. So there will be a change in direction of velocity in this direction approximately. And it is this change in direction of velocity that we now want to find an expression for, which then will be the magnitude of the centripetal acceleration. And to get an expression for this change in direction of velocity, let's take these velocity vectors and give them the same origin, which basically means that we take one of these vectors, for example, this final velocity vector, and shift it along the trajectory towards the origin of the initial velocity vector. So we know that this was vi and this was vf, but now they have the same origin. Now, why did we do this? Well, because at this point we see that we have here the vector connecting both ends of these velocity vectors. This will of course be the vector dv, the change in direction of our tangential velocity. And we see that these three vectors now make a triangle, and a triangle is something that we can work with. However, in order to be able to work with this triangle, we need to find this angle right here. And to find this angle, we note that the tangential velocity will always be perpendicular to the trajectory, therefore perpendicular to the circle. So this angle right here and this angle right here will both be right angled. And because both of these angles are 90 degrees, we know that this angle right here, the angle between this line and this line, will be equal to this angle between these two velocities. So this will also be the angle d theta. And again, this is only the case because both of these tangential velocity vectors are perpendicular to the trajectory. What we can do now is the following. Let's remember that this formula, ds is equal to r d theta, can now be applied to the triangle on the right. We have that the magnitude of dv is equal to the magnitude of our velocity, which does not change in time because we are looking at uniform velocity. And this basically corresponds to this distance, the length of this vector, multiplied by d theta. And before we go on and get a nice expression for the acceleration, let's first look at this formula and see whether it makes any sense. We see that if we are traveling along the trajectory with a much larger velocity, so the magnitude of the velocity, the more change in direction of velocity we need in order to make a circular trajectory. Now let us also remind ourselves that the magnitude of the tangential velocity can be written as follows. So the magnitude of the vector v is equal to capital R, the radius of our circle, multiplied with d theta over dt. So basically r multiplied by omega, the angular velocity. And we can rewrite this formula right now to get that dt is equal to r multiplied by d theta divided by the magnitude of the tangential velocity. And why we did this will be clear in a second. So let us now get an expression for the centripetal acceleration, or more notably, the magnitude of the centripetal acceleration, because we already know that it will be always pointing towards the center of the circle, but that I cover in another video. So this will be equal to the magnitude of the change of velocity to t, but we now have a formula for this magnitude in change of velocity. And this is simply equal to the magnitude of the velocity times d theta, and we divide this by dt. And what we will do now is use this relation of dt as a function of these terms right here. We simply copy the magnitude of v multiplied by d theta, the change in angle, and we divide this by r multiplied by d theta divided by the magnitude of v, which is simply this side right here. We see that d theta cancels out and this v can be brought to the numerator. In this way we get the magnitude of our tangential velocity squared divided by r, the radius of our circle. And this is exactly the formula that you probably already know, that the magnitude of the centripetal acceleration is equal to the centripetal velocity squared divided by the radius r. Let us now conclude with a brief overview of the 3 types of acceleration that we found in this video. And as always, we start with drawing our circular trajectory with a radius r. If we find ourselves in this point right here, and we don't assume that we have a uniform circular motion, because we know that then only the centripetal acceleration will be present, then there will be the following accelerations. We have, of course, the tangential acceleration, which will be tangential to the circular motion, and which basically say that we're speeding up along our trajectory, making laps in an ever-increasing rate. We found that the magnitude of this tangential acceleration was simply equal to the radius of our circle multiplied with the angular acceleration. Which brings us, of course, to the angular acceleration, which is the rate of change of the angle that we are making. And again, to recap, the angle that we are making is this angle right here. And what is special about the angular acceleration, and is the same for the angular velocity, is that it does not depend on the radius r, and in this way a more fundamental quantity. And as the last type of acceleration, we have the centripetal acceleration, which is always present in circular motion even if we are not speeding up along our circle. So the tangential and the angular acceleration are 0. So this will be the centripetal acceleration. And as we found in the last part of this video, the centripetal acceleration's magnitude will be equal to the tangential velocity squared divided by the radius of the circle. And these are the 3 types of acceleration that you could have in circular motion, but in reality these first 2 are bunched together because they are simply related by a multiplication with the radius r. And this last acceleration will always be present, even though you're not speeding up along the circular trajectory. And this brings us to the end of this video, and I hope that you now have a better overview of the different types of acceleration that can be present in circular motion. If you have any questions, leave a comment in the comment section below or join our Discord server. If you enjoy these videos and you appreciate the work that goes into them, consider giving them a thumbs up, which helps me out tremendously. And with that, I thank you for watching, and I will see you in the next one. Bye.